Hi everyone, we're the GPS-based autonomous navigation team from the autonomous vehicle subdomain. My name's Nagina, and these are my teammates Garrett and Chian. We're going to start off with the question, why GPS-based navigation? And aside from the fact that it's common in autonomous vehicles to use a GPS as a component of their navigation stack, it's also very necessary for global localization. And that's simply knowing where you are on a larger scale. While other sensors on our vehicle might be able to determine a more local understanding of where we are, it's necessary for the GPS to be there because we need to know where we are on a global scale. I'm going to quickly go over some of the pitfalls of a GPS. And the main pitfall that we wanted to highlight was that signal quality can be drastically impacted by surroundings. And typically these surroundings can be things like buildings or just anything that might cause interference with the satellites. And these issues can cause lower precision and slower messages. So the challenge of GPS-based navigation is that we have no awareness of our current surroundings. So if there's an obstacle ahead of us, we can't avoid it because we can't see it with just a GPS. However, this is why other teams within our subdomain are working on things like computer vision and optical avoidance. So our goal for this project has been to create a GPS-based navigation for an autonomous vehicle that we could integrate with our subdomain's work. And our subdomain's goal had been to create a well-rounded functional autonomous vehicle.
All right, so the first step in building an autonomous navigation stack, we had to choose a reliable GPS to fit onto our vehicle. And then we had to do sensor fusion to fuse readings from the multiple sensors that we fit, like IMU, odometry, and GPS. And then the third step is path planning, which is just generating the full global path. And then lastly, we need to get the vehicle to navigate autonomously, and this is just called Waypoint Navigation. So as was mentioned before, GPS data can be pretty unreliable at times. Even if the GPS was physically at a certain longitude and latitude, it might actually output a position that was slightly off from that latitude and longitude. And to test the accuracy of the GPS, we can use two metrics to do so, circular error probable and 2D root mean square. So circular error probable, or CEP for short, is basically a radius of accuracy from the true coordinate point 50% of the time. So that means that if we tested a GPS and it yielded a CEP of 5 feet, then we will know that for half of the time, we can expect our current GPS reading to be accurate within 5 feet of what its actual position should be. And 2D root mean square, or 2D RMS, is similar to CEP, and that's also a radius of an accuracy radius from the true coordinate, but 95% of the time instead of 50% of the time. If a GPS has a 2D RMS of 10 feet, then we will know for 95% of our readings, we can guarantee that's accurate within 10 feet of the actual position. And our procedure to test the GPS is basically as the flowchart says. We turn on the GPS and we let it calibrate for a few minutes. And then without moving the GPS, we leave it at a stationary position so that we can record its position readings. And then we translate these readings into UTM coordinates, which has an X and a Y component and is measured in meters. And we do this because we want to get units for the radiuses that we calculate, like a CEP radius of like 5 meters or so. And we can take an average of all of these readings to be our truth value, and we find the average deviation of each reading from the truth value. And we do this for both the X and the Y component. And then we can just input these into the CEP equation and the 2D RMS equation.
So moving on to evaluation on our after modules, the first one that we started off with was called the uBlocks Neo M8N. So for context, this is approximately just a $15 off-the-shelf commercial module that anyone can pick up at a hobby store. So when we evaluated this, going through those testing procedures, we found that we got a CEP of approximately 1.5 meters and a TD-RMS of around 3.7 meters. On the scale of a 1/10 or 1/5 vehicle, this is most likely not going to be sufficient because the car itself is much smaller than those two metrics. So we really won't even be able to determine where the car is on the road or wherever it's going to be driving. The next module that we wanted to test is called the ZF9P module, which is enclosed in this C099 F9P application board. So the board as a whole is just a carrier unit to allow us to more easily connect to it get sensor readings, and attach different types of antennas to it. So this ZF9P GPS is supposed to be a lot more performant. So we thought it was a really good module to actually test some of the downfalls of a GPS. In order to do this, we wanted to compare the performance of the GPS in a neighborhood where there's tall buildings, where the actual signals will bounce off of those walls and go back to the satellites, and compare this to just the GPS in an open park. We found that the performance differed drastically. As we can see between these two plots here, in the neighborhood, the CEP was around 3.5 meters with a 2D RMS of over 9 meters, compared to a park setting where the CEP was actually just under 10 centimeters with a 2D RMS of just over 0.2 meters. So this is very surprising to see how drastic the difference is. But for our case of navigating in an open track, we can expect the performance of the ZF9P that we get while it's inside of the park. For a little bit better context here, we can actually see how much the actual CEP changes on the scale of the two different models here. So the original blue lines here represent the actual drifting GPS of the same ZF9P in that neighborhood, where we can see that it's moving all around everywhere we go, and we really don't know where it is, compared to the precise and accurate location data that we're getting from the ZF9P when it's in an actual park. Once we actually determined we can use the ZF9P module, we needed to figure out how to fuse this data with both the odometer data and the inertial measurement unit data. To do this, we were going to use an extended column filter, which is a state estimation algorithm, which will eventually give us a more accurate position and orientation. These different modules themselves, the GPS, VESCA, and IMU, each give us their own respective data types. In the GPS, we get latitude, longitude, altitude, but for a car that's only going to be hopefully driving on the ground, we really don't care about altitude. For the VESC, it's calculating position and orientation based off of just the linear velocities here. So we really only want to care about those raw linear velocity data in the X and Y components. The IMU functions in a similar way where we get the acceleration data as the raw values. So we don't really care about the velocities that are calculated and the orientations that are calculated, because these can just be derived. Unfortunately, when we actually combined the IMU and the GPS on the real modules, we found that the IMU just had too much noise in the linear acceleration data points. So because of that, we actually ended up getting worse performance when using those values. So to conclude that with that, we just decided to not use the X and Y linear acceleration values and just use the C component for angular velocity, which will allow us to get the actual heading that we need. As a way to actually see how the GPS module performs throughout the EKF algorithm, we can see on the left side we have simulated noise of the NEO M8N GPS, and even after going through the EKF algorithm, we can see here that the purple sphere represents the possible positions that the actual car can be in. In the case on the left, we really don't know where it is on the track or even what point it's really at. There's just too much noise in it still, and it really can't be used at this scale. Compared to the right side with the ZF9P, it's a lot more precise, and we know exactly what waypoint it's at, as well as exactly what part of the track it's actually at. So once we have this sensor fusion completed, then we can move on to the path planning component. So for our subdomain, the original goal was to actually eventually race on the Thunderhill Raceway Park track in Northern California here, which is what this picture is on the right. So in order to implement path planning, we need to start with a global map. So similarly to how in real life you need a map to get from point A to point B, we need a map to be able to navigate autonomously. For us, this map is just a simple binary mask, where white represents allowable regions to drive and black represents essentially boundaries where we don't want to be going. Once we have this map, then we want to be able to determine some feasible path for the car to navigate. Luckily, since this is a real racetrack with cars that have actually driven on it before with different sensors, we can actually just use some of the GPS data that's been collected in the past, which is what all these blue data points here now are, and then eventually just determine what is a path that our car can execute on this path. The original data set that was used here is over the course of many, many different laps of the car going from start to end and also going through different subparts of the track. So we also have to do some filtering here where we remove the beginning and ends and average the points to eventually just determine one single lap with just the amount of waypoints that we need to complete that lap. Once we have this full path, then we can actually move on to the waypoint navigation section.
So now we can go on to the last step of the process, waypoint navigation. And what we do here is that we collect some waypoints and we compile it into a list in the order that the vehicle would encounter them. Basically, you can kind of think of waypoints as just points of references. If you want to get from point A to point Z, we can find points B, C, D, and so on that lie between point A and point Z. And between any points, we can actually find a straight path connecting them. So we can just give these waypoints to the vehicle and tell it to travel down the straight path between waypoint B and waypoint C, and then from C to D, and so on until it reaches the end. So this is the path that we generated after we collected some waypoints on our track. And this is not the Thunderhill track, but a track that we had access to at UCSD. The purple arrows represent the location of the waypoints, and the gray path is the actual track. The green line is a generated straight line or straight path between each pair of waypoints. And with enough waypoints, these straight paths can actually follow the curve of the track pretty well. So you can see that generally, by connecting the paths between each waypoint, it makes a pretty good course for our vehicle to follow through to complete a lap on the track. So now that even though we have a predetermined list of waypoints, it's actually not as simple as saying, okay, we're currently at waypoint B and now we can head towards waypoint C. And it's not that simple because, as we established before, GPS data can be pretty noisy. So even if it has physically arrived at the coordinates of waypoint B, the vehicle itself may not actually realize that because the GPS is outputting a coordinate that's like off by a foot. So how can the vehicle know which waypoint to head towards, and how can it tell if it has already reached a waypoint? Basically, we just run through an algorithm that is listed in the flowchart here. So it just calculates the distance between the current vehicle position and a look-ahead point. And a look-ahead point is just a waypoint that is some amount of spaces ahead, like 3 points ahead. So each waypoint will have a different look-ahead point. We also want to calculate the distance between the current waypoint, waypoint X, and the look-ahead point. For an example of how both of these distances are calculated, you can refer to a diagram on the left. Okay, so after calculating both of these distances, we perform a simple check. Is current position look-ahead distance less than the waypoint look-ahead distance? If this is false, then that means the distance between waypoint and look-ahead is less than the current position and look-ahead. So we know the vehicle has already reached the current waypoint, and it should be heading towards the next waypoint, X plus 1. But in the other case, that distance waypoint, the distance between the waypoint and the look-ahead is greater than the distance between the current point and the look-ahead, we know that the vehicle has not reached waypoint X yet. And it should steer towards waypoint X. So if it has not reached waypoint X, what it should do is keep steering towards X while continuously calculating the distance between its current position and waypoint X. Now, as we mentioned before, noisy GPS data is a problem because we can't guarantee that it will output the expected coordinates even when it's physically at a certain coordinate. So to fix the problem, we set a buffer radius around waypoint X. And you can refer to a diagram on your left to see how that might look like. So if we set the buffer radius to the CEP or the 2D RMS of the GPS that we're using, because that is the inaccuracy radius that we expect our GPS positions to have on average. And if the distance between the current position and the waypoint X is less than this buffer radius, then we know the vehicle has a good chance of already having reached waypoint X. And we could just head towards the next one, which is waypoint X plus 1. So now that the vehicle knows how to choose which waypoint to head towards, it needs to know how to navigate between these waypoints. At this point, waypoint navigation is just 2 things, steering angle and throttle. At each waypoint, the vehicle needs to calculate what the steering angle should be set to arrive to the next waypoint, waypoint X plus 1. For steering angle, we can just check if the current vehicle heading, which is information that we can get from the IMU sensor, and check if that's equal to the waypoint orientation. If current vehicle heading is not equal to the waypoint orientation, then it needs to rotate, and we can just use the PD controller to determine the heading the car needs to be at to point towards the waypoint. But if they're the same, then there's no need to change the current steering angle because the vehicle is already pointing towards the waypoint.
So after doing all of these steps of our navigation stack, then we're finally to the point where we can actually implement it on our car and see how it performs. So on the top left here, we can see the actual generated path that we talked about earlier. And we're now watching the car try to actually navigate with the controller that we had, navigating from waypoint to waypoint here. An interesting fact about this is, as we talked about earlier, a GPS on its own is blind and has no global or no local awareness of its surroundings. So if you actually can look at this map on the top left, it did actually go out of bounds, but because there's no other sensors being used right now, the GPS doesn't tell it to do anything, and the car just keeps going wherever it wants to go here. So with that, this concludes the scope of our problems with the GPS-based autonomous navigation here. Before we go, we'd just like to thank a few different people. First off, our domain mentor, Professor Jack Soderman, did a great job of teaching us and supporting us over the past 2 quarters. Along with him, we'd also like to thank our TAs and also the other teams that we had a chance to work with over the course of the past few months. And finally, we want to thank HDSI for both funding this class and allowing us this hands-on experience in this unique time.